is putting the P back in VPN, correct? With Roger here. And there is one change we need to make an announcement about. During this block, next door will be Richard Theme and not Ophir. Ophir couldn't make it in, so if you're a big Richard Theme fan, head on over. And if not, stick around for Roger's talk. And you ready? All right, here's Roger.
Okay, I'm Roger Dingledine. I'll be telling you a little bit about anonymity systems, in particular low latency ones. So who here has heard of the Zero Knowledge is Freedom Network? A couple of people. Who here has heard of mixed networks? A couple of people. Okay, sounds good. Well, I'll give you all sorts of background on all those things, and hopefully by the end you'll be convinced. Okay, so basically I'm going to talk quite a bit about anonymous communication, and some people think of that as traffic analysis resistant communication. It really depends who you're talking to. I'll give you a little bit of idea about what sort of properties you might want from a system and how you get them and whether you've gotten them. I'll talk a little bit about some building blocks that you can use to actually achieve privacy. Then I'll talk mainly about a system called Tor, the Onion router, which I've built and deployed, and it's free software and you can grab it and use it. Then I'll talk about some more features about it, and we'll go from there, and hopefully there'll be time for questions. Okay, so the basic idea here, a lot of people say, well, I use encryption, I'm safe. But if you go to Central Park and you log in and you use your VPN to your home company and it goes from you to your home company, then everybody says, aha, he works at this company. And that's if you're lucky. If you're a CIA agent and you go to Venezuela and you log into your home CIA machine from your VPN, then everybody says, aha, he's a CIA agent. So in this sort of situation, you don't just want the encryption, you probably want some more protection. Okay, so there are plenty of different classes of people who might want privacy protections. We've got the usual socially sensitive communicants. If you have cancer or something, you might want to talk about it without having your boss say, oh, he's got cancer, let's fire him. Political dissidents and whistleblowers and so on, censorship-resistant publishers. But there is also a strong law enforcement need for this sort of thing. On September 12th, 2001, the anonymizer set up an anonymous tip line to the FBI, which was used. And the FBI was happy about it, and an anonymizer was happy about it, and so that's a beneficial thing for national security. Corporations also care, because if you're going to buy tires from a certain place every day, then somebody else wants to know who you're buying tires from, and they can maybe bribe a janitor or your ISP or whatever it takes, and then they know where you're buying stuff from, and maybe you prefer to keep that a business secret. Or you can use it to anonymously check out the website of your competitor without having him say, oh, they're looking at us again, and they spent this much time on this page and this much time on this page, and so on. Okay, and if that doesn't convince you, think about actually people double-click or whatever, keeping track of where you go every day and figuring out, oh, you work over here, you live over there, you're probably interested in race cars. Maybe you shouldn't get that sort of car insurance because you did buy that race car book at Amazon 2 years ago, or something like that. And government. I should mention at this point that I'm paid by the United States government to build anonymity software. And a lot of people say, well, why would they do that? They don't think of it as anonymity software. When I talk to researchers, I talk about building anonymity software. When I talk to my parents, I build privacy software. To corporations, I build security software. And I'm selling to the government traffic analysis resistant communication networks, which they clearly need because they need to be able to talk and resist traffic analysis. So they don't think of it as anonymity, they think of it as the security that they need. And there are all sorts of different ways that we've been pitching it to them. If you need to do open source intelligence gathering, meaning learning about other stuff from websites and so on, then you need to be able to hide the fact that you're coming from a .gov address or a .mil address. If you have a classified network, the SIPRnet has more than 1 million people on it. It's secure and classified. It can't possibly be secure with more than 1 million people on it. It's crunchy on the outside and chewy on the inside. You might want defense in depth, some sort of internal overlay network that stops some observer from knowing, oh yes, the general just went to this country and people are talking to him there. And there are all sorts of other approaches, dynamic coalitions if you want to work together with Mexico this week, but plan to be their enemy next week, then you might want to not tell them all about the topology of your networks. And road warriors, procurement patterns, and so on. All these slides will be up on the website. And every time I talk about anonymity, people say, well, aren't you going to destroy the world? You're going to let all the terrorists communicate anonymously, and you're going to let people send spam everywhere, and it'll be untraceable, and everything will go to hell? Criminals already have this technology. Criminals break into a machine in South Korea and use that to break into a machine in China and then Afghanistan and so on, and then they attack you. And they're doing just fine breaking the law in order to break the law. We're trying to build a technology here where honest people have the ability to get privacy. Feel free to jump up and say, no, I disagree, or what do you mean by that, or anything like that, so we can make this a bit more interactive. Because if you've got a question, chances are the guy next to you didn't understand it either. Okay, so a little bit more about anonymity. Anonymity loves company. You can't be anonymous by yourself. If you've got encryption software like PGP, Alice and Bob sit down and they say, I would like to anonymously send mail to the other one. So assuming they use the software correctly, they get the encryption. Somebody watching it doesn't know what they've said. If Alice and Bob sit down and say, I want to anonymously send mail to Bob, then Alice can't do that by herself, because if she's the only one who has the software and somebody watches Alice send something and it ends up at Bob because those are the only users in the system, then she doesn't get the security she's looking for. So anonymity needs other users. The Navy can't just deploy an anonymity system for the Navy, because if it did that, then only Navy people would come out of it, and people would say, oh, that's the system the Navy uses to anonymize itself, ha ha. So you need to pass traffic for other people, not related to yourself, but perhaps doing similar things, so that you have somebody to blend with. And that's the reasoning for distributed trust. Because if I build a system and I want you to use it, and I'm the US government, you're not going to use it. You're going to say, why should I pass my traffic through the US government when I could just be going directly to the website? So you want to have other people running nodes in the system also, so that your traffic goes through them also. So traffic moves through multiple nodes, and you don't have to trust any one of them to protect the source and destination of your traffic. Okay, so what are we talking about here? Anonymous from who? If you want to protect from the recipient of your message or the sender of some message to you, then you need channel and data anonymity. You need not only to hide the location of where the stuff was coming from, but you also need to make sure you didn't put your name in the channel itself. Because if you go to Amazon and say, I'm anonymous and here's my credit card number and name and address, then you are in fact hiding the location you're coming from, but that may not be what you're looking to hide. On the other hand, if you're just talking about an outside observer or an insider in the network, then maybe channel anonymity is enough. It makes perfect sense to SSH in a bidirectionally authenticated way over an anonymous channel. And what you're getting there, Alice is talking to Bob, you're getting somebody watching Alice doesn't know where Bob is or which Bob she's talking to. Somebody watching Bob doesn't know where Alice is coming from. And somebody running a node in the middle doesn't realize that it's Alice talking to Bob. Okay, so what we're doing here is just location anonymity. We're not talking about data anonymity. You have to use other means to make sure that you're not signing your name or putting the exact version number and build time of your browser or whatever into the channel. Okay, so at this point, for people who already know a little bit about mixes, I'm going to, for people who don't know anything about mixes, I'm going to give you a brief overview. For people who do, there's a URL there. I believe the net works in this room. Go grab the code and install it and use it, and get back to me in about 10 minutes, and hopefully you'll have it working by then and you'll have better questions. So it's published under a free license. It's not encumbered by a patent, which was a big problem with a previous generation of onion routing. It works on everything under the sun. It's packaged for some things under the sun. It runs in user space. You don't need to be root. You don't need to mess with your kernel. It's just an application. You get it, you use it. Okay, so there are a bunch of different approaches for getting anonymous communication. Basically, there are two categories. There's high latency systems called mixes, which are used for email or something where people can tolerate a couple hours delay. And there are low latency systems where people are going to web browse or something and they really don't want to wait 2 hours for their web page. So the high latency stuff, mixes. So imagine you've got a node somewhere on the internet and a bunch of people send mail in it decrypts the mail and shuffles it around and sends it out. So the idea there is that one of the messages on one side corresponds to some message on the other side, but the adversary isn't able to figure out which one is which. So how does this actually work? We've got 3 servers here. You've got yellow and red and blue keys. And the idea is you want to send a message through all 3 of them. So you wrap up your message with the public key of the last one, and then wrap that up with the public key of the middle one, and then wrap that up with the public key of the first one. So the idea here is if the adversary doesn't know all 3 keys, he can't just open the message and say, aha, this is what it is. And then you send it to the first one, and he pulls off the first layer and learns, I should send it to this one, sends it to that one, and he pulls off the next layer. And without the particular key involved, you're not able to unravel the message any farther. Okay, so the way this actually works is you put several machines in a row. One of them should be enough to provide your anonymity, assuming you trust it. But if you don't want to trust it, then you use several of them so that any one of these can provide the security you're looking for. So 3 messages come in. Server 1 decrypts them, takes off the yellow part, shuffles them around, sends them on to server 2. He takes off the red part, shuffles them around, sends them on to 3, and then so on, and then they get to their destination. So server 3 knows that 3 messages went out, and here are the messages. And if they used end-to-end encryption, then he doesn't know what they say. And server 1 knows that 3 messages came in, but nobody knows, even if server 2 and server 3 are bad, which one was message 3. So far, so good? Okay. So that's all fine and good if you're talking about email anonymity. But what if you're trying to anonymize your SSH or your AIM or your web browsing or something like that? You really don't want to wrap it up in a message and then send it on and wait for an hour while somebody shuffles it and sends it farther. So each layer of the message requires public key crypto, and it also requires delaying so that you have enough messages together to batch and then send onward. So the basic approach here is a proxy. I'm sure all of you are familiar with the basic notion of a proxy. You start here, you go there, and then you end up where you're going. The anonymizer is an example of this, where people start at whatever cable modem system they're on, and then they send their traffic to the anonymizer, and it sends it to the web server, and then back to the anonymizer, and then back to the client. So this is all well and good. If you trust the anonymizer, then you're pretty much done. But what I mean by trust the anonymizer is not only trust that they don't have any bribable janitors, but also trust that they're not going to sell out your data or deal with a subpoena order that you would rather they not obey or something like that. There are all sorts of points of failure here that you really don't want to trust, depending on your traffic. So what we do here is we combine the advantages of both systems. Mixed systems are slow, but they have good crypto and good security. And the proxy systems are fast, but they have pretty much no security. And what we've done is we've used the multiple hop distributed trust idea and the layers of crypto idea, but we don't worry about mixing, and you just use the public key crypto, the expensive stuff, to lay the circuit, and then you use the cheap crypto to send all your data back and forth. And I'll tell you in a bit exactly what I mean by that. So there's lots of related work. This isn't the first this isn't the first system to use this sort of idea, and I'll tell you a little bit more about how the related work relates towards the end. Okay, so the basic idea here for onion routing is we've got an overlay network. There are 30 or so computers around the world. 20 of them are in the US and 10 of them are in Europe. And people download the software and they figure out which machines are on the network right now and what their keys are and which ones are up and so on. And they build circuits through the network. There's an example network there, and I'll show an example of actually constructing a circuit in a bit. So you've got a proxy on one side, and it deals with doing everything the client needs to do. So when I say the client does, I actually mean the client software does. Okay, so the system's called Tor. I talked to a lot of people at the beginning, and they said, well, what are you working on? And I said, oh, I'm writing onion routing. And they said, oh, really? Which one? And I said, no, it's the onion routing project. It's the original one. And they said, oh, I'm confused. So I renamed it to Tor, or the onion routing system, because it's the onion routing system. Or if you prefer recursive acronyms, we've got one of those too. Okay, so the basic idea here, you got your overlay network on the internet, and the client establishes a Diffie-Hellman ephemeral key, forward secret, and so on with the first one. And then from there, he extends it So he connects here, and then he tunnels that to the second one, and then he tunnels that to the third one, and so on. And the idea here is that he has a key that he shares with each next hop, but the next hops don't, the purple guy doesn't know where the client is. He just knows that there's a green guy and a dark green guy that he's connecting between. Okay, and from there you can send a begin cell or something tunneled through the network. And the way you actually send the cell is the client builds the data cell that he's going to send, and then encrypts it with all three keys. And he sends it to the first one, that one pulls off one key, sends it to the second one key, and so on. So by the time it comes out the end, it's in plain text. Or if you're using end-to-end encryption, then it's encrypted to the web server. So you can connect to a web server, then connect to another one, and stop using one, and so on. And all of this is multiplexed within the same circuit that you've constructed. And of course, you want to construct more than one circuit over time, because if you hold one open, then maybe somebody can take their time tracking it from one hop to the next. Just like in the Sneakers movie when they have the satellite thing up there and you're watching them track from one satellite to the next across the world. Okay, so how do you actually connect to the network? What's going on here? We've got directory servers to simplify that. So when the code ships with the keys and the locations for special servers, which keep track of who's in the network and who you can trust and what their keys are and where they are right now and so on. And the reason why we need to keep humans in the loop here is the adversary could show up and say, hey, I've got a server that would be really useful for you, and I've got another one, and these other 6,000 would be useful for you also. And pretty soon, if there are 6,030 nodes in the network, and 6,000 of them are run by the adversary, we're probably going to choose a bad node at every hop. And if we choose a bad node at every hop, then we're pretty much screwed. So what we need to do is actually pay attention to which servers are joining the network and say, didn't you sign up this other server over here from the same IP? What's going on? And for the most part, we haven't had problems with that. Mostly, I think, because we actually require them to send us email, and probably the adversary realizes he'd look pretty dumb trying to sign up 30 nodes when we were manually verifying them. And also, the directories are not a bandwidth bottleneck because they're cached onto every other server. So you can go to any server and get a directory, and it's signed by one of the directory servers, so you know that you're getting a legitimate one. Okay, so some properties here. It's written in C. It's 26,000 lines of code. It was 19,000 a little while ago. It's growing slowly, but it's still reasonably small and reasonably efficient. The servers run in user space. There's no need to be root, no need to mess with your kernel and so on. That was one of the big problems with the Freedom Network, because you actually have to install a kernel shim, and it all turns bad when you upgrade your kernel. So we work on everything. We're portable. We even work on Win32 now. We just anonymize the pipe. If you want to web browse over this thing, then you probably want to use a proxy such as Provoxy, which removes your referrer log and removes your cookies and whatever else would identify you. We work with SOCKS. The SOCKS protocol basically lets you say, this is the address and port I want to connect to. So Mozilla has it already built in, and most things have it already built in. So you can connect with your Mozilla or whatever without having to modify it at all. And we have exit policies on the server's side. So you can specify, I want to allow web traffic out and AIM traffic out, but I really don't want to allow port 139 because that would just lead to trouble. So some of the servers are running in middleman status, meaning they aren't allowing anything to exit from them. And some of them pretty much allow anything. So if you want to run a server, that'd be great, and you can tune it based on whether you have lots of bandwidth or whether you would like to deal with lots of abuse issues or not. Okay, so it works in all sorts of places. One of the neat things about Tor over the previous onion routing design is that we use the same circuit to handle multiple TCP streams. So in the past, if you went to CNN.com and you pulled down the HTML and then you pulled down 45 images, you would build 46 circuits. And each of those would require public key operations to build it. And so it would be really quite slow. Also, when you're building a whole lot of circuits like that, somebody who owns maybe 20% of the nodes in the network can watch where all of these circuits are being built from and say, hey, you know, that guy seems to be building a lot of circuits right now, and somebody over here seems to be pulling down a lot of images from CNN. So you really don't want to build as many circuits as we were before. So we fixed that by multiplexing them. And also, you use a circuit for a little while, and then once a minute or so has passed, then you say, hey, that one's too dirty, it's too dangerous, I'm going to start building another one. So you want to build the circuits in the background so that the public key operations don't actually impact the user. Okay, so we've got rate limiting for bandwidth, so people running servers don't have to donate all of their bandwidth to it. And that we've also used a token bucket approach so that you can allow spikes in the bandwidth and still maintain an average that you would like to have. We've got flow control. One of the interesting things about the old onion routing design, and a number of other systems fall to this as well, is what's called a tagging attack. So imagine you've got Alice on one side and you've got Bob the web server on another side, and Alice is Bob the FTP server on another side, and Alice is logging in and so on. So without integrity checking on these things, imagine Alice sends DIR to the FTP server, and some guy in the middle pulls out DIR and puts in RM star, and the cell makes its way to the end, and that's what's executed on the FTP server. So the way this actually works is we were using stream ciphers without any integrity checking. The way a stream cipher works is both sides start with the key, the cipher, and they generate a stream of text that they're going to XOR the plain text with. So Alice starts out and says, this is the key text, this is the plain text, and then you XOR them together and you get the cipher text. But the problem with XORing is that you don't actually have to know what's inside. The adversary can't read it because it's been encrypted with the stream cipher. But he can guess, I bet those 3 bytes are DIR and that one's a null. So he can XOR that out, XOR in his text that he would prefer to have. He still can't read it, but he's now changed what it says. So that's an attack that works on all sorts of crypto systems unless people put in integrity checking, which we did, so hopefully that one's solved. In the past, the reason why it's called onion routing is because previous versions of this sort of software built up what's called an onion, a layered data structure. So Alice starts here and builds that thing that's surrounded by all the layers of colors, and that specifies where the path is going to go and which keys are supposed to be used at each path. So then she builds up the whole onion and just throws it into the network. It makes it to the first hop, which decrypts it by 1 layer and notices, oh, I'm going to go here, sends it there, it decrypts it by 1 layer, and it works its way through the network. And by the time it's done, then the onion's gotten really small and it's done, and then Alice can use that circuit. So the problem there is that each of these layers of the onion has the key that Alice is going to share with that node in it, because there's no way for that node to talk back to Alice and negotiate a key that they both participated in building. So that means that if the adversary intercepts the onion, he can use it later and send it again, and it'll build the same circuit. Or he can go 1 hop at a time and break the kneecaps of each server until they reveal where the next hop is. So even a week or 2 later, he might be able to track it down. With the new design, where we sort of build a telescoping circuit, you don't have to deal with replays anymore, and you also get perfect forward secrecy because you're negotiating a key with each hop as you go. And as soon as he's negotiated the key, he throws away everything he used to build it. So there's no way for him to reconstruct it, even if you show up later with everything that you logged from the network. And also, maybe we can adapt to dynamic networks a bit better, because while you're building a circuit, you know which node was down when it fails to extend. Whereas with the onion, you throw the onion to the network and it says, sorry, it failed. And who knows where it failed or what happened. Okay, so a couple of years ago, we had an original version running, and this was pretty much centralized, running at the Naval Research Lab. It handled something like 50,000 web requests a day, so there is clearly a want for this sort of technology. The next generation one, we've been running it since October, and we've got 30 nodes around the world. We have maybe 40 users. We have maybe 2,000 users. It's an anonymity system. I really don't know. I would guess that it's somewhere in the 1,000 range, but I'm just making that up. Each node processes somewhere around 1 gigabyte a day, so somebody's producing and using traffic. And it's up from 0.5 gigabyte a week from just a little while ago, so it's starting to take off. The network's never actually been down. That's one of the nice things about a distributed network. Even when some of the directory servers are down, the other nodes are still reachable, so you can continue to use it. And this isn't entirely true, because if the site that gives you the source code is down, then people who already have it are okay, but people who don't have it obviously can't fetch it and use the network. Okay, and some latency tests just to show that it doesn't suck too much. If you're pulling down CNN, usually you can do it in 0.3 seconds from a really fast machine. And if you're using it from Tor, then you have the whole web page after 2.7 seconds. So there's some latency that it adds, but if you're willing to wait a couple more seconds, then you get your web page. And it's reasonably reliable at this point. Okay, so let me tell you about another system that we've got. I've been talking so far about maybe Alice wants to get anonymous from the website or from some observer. She wants to hide her IP from the adversary. Imagine now that Bob wants to run an Apache server, and he wants to allow Alice to connect to it without knowing what its IP is, without knowing where it lives. You could also imagine this as the US military wants to give out orders to its military divisions, but it doesn't want to reveal the location of the orders server, because then the adversary would launch a bomber and take out the city, and that would be that for the server. Now, you could take the Akamai approach and buy 8,000 computers and put them all around the world and hope the adversary doesn't actually take out every one of them, but that's really quite expensive. The approach we have is you can provide a hidden server, which the adversary can't find the location of, and then also a public server, and you tell your people about both of them, and when the public server gets bombed, then they start using the hidden server. So for the most part, they get high performance on the public server, and then you only have to buy a backup server rather than 7,999 backup servers. So the idea here is that you can get to them from anywhere, and they resist censorship, and also one of the nice things is that they resist DDoS attacks, distributed denial of service, because nobody knows who to DDoS. That's the theory, at least. And there's some issues here, because the answer is, well, gosh, you just take down the onion routing network. You just hit all the Tor servers, and then, of course, you can't get to the hidden server. But there are 30 Tor servers now, and they're located in coloc facilities around the world, so they're a little bit hard to hit all of them. And there might be 100 or 200 or 1,000 of them later on, and hopefully that would be quite hard to hit. So how does this actually work? The simplest version I can describe is, let's say Alice wants to talk to Bob, and Bob wants to remain location hidden. So he onion routes out to some rendezvous point and says to the world, if you want to talk to me, Bob, here's my key. Go talk to this rendezvous point, and I'll be listening there. And then Alice learns that, and she onion routes out to it also and talks to it, and they're all happy, because Alice is talking to Bob but doesn't know where Bob is. And incidentally, Bob doesn't know where Alice is either. The problem with that is Bob advertises, if you want to talk to if you want to get to my content, go to this onion router. And I talked to people who were going to be running onion routers, and they said, no way am I going to offer a service like that. Bob's going to offer some horrible thing like criminal activities or whatever, and my node is going to be associated with that. Not only associated with it, but my node is going to be serving the criminal content. No way am I going to run that. So we add another layer of indirection, and I'll tell you exactly how that works here. So Bob picks a bunch of introduction points. These are nodes which are willing to be associated maybe with the public key of Bob, but they don't actually serve any of Bob's data. So Bob connects to all of those over the onion routing network and says, if anybody wants to talk to this key, that's me, I want to talk to them. Then separately, he goes to some out-of-band thing and publishes a list of his key and his introduction points and signs it. And possibly you can add some more stuff there. And there are many ways of doing this. Right now, basically the directory servers receive it and then give it off to other people. So he onion routes out to some place and publishes a service descriptor. Alice fetches the service descriptor, and this means that somehow out of band, Alice needs to know some summary of Bob. The way this is actually implemented is we use a top-level domain .onion, and then the host name is the base 64 of the hash of the public key. So Alice has blah, 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 .onion, and she clicks on it in her Mozilla, and the Mozilla sends it to the Tor client locally, which looks at it and says, this is a .onion address, clearly it's for a hidden server, and it goes to the lookup system and pulls down the service descriptor, and then she goes on to the next step, which is she picks a rendezvous point. Bob doesn't know about this yet, but she onion routes out to it and says, if anybody wants to talk to this one, then I want to hear from them. And then she connects to any of the introduction points and says, this is my rendezvous point. I'm Alice if you want to talk to me. And then the introduction point sends it back to Bob. So notice at this point that the introduction point has sent nothing to Alice, and it never sends anything to Alice. It doesn't even have to acknowledge that it got the request. So Alice doesn't necessarily have to know what was going on. In the current implementation, the introduction point either says, yeah, okay, or who the heck is Bob? Because that makes it a lot more easy to actually use. But we could imagine a situation where Bob doesn't want to even, or the introduction point doesn't even want to reveal that he's associated with it. So at that point, imagine Bob looks at the statement, I'm Alice, and says, oh yeah, it's Alice, I want to talk to her. So he onion routes out to the rendezvous point, and then the rendezvous point connects them together. So now Alice and Bob are talking over a rendezvous point, just like they were before, and the rendezvous point doesn't know who Alice is, doesn't know who Bob is, and since Alice and Bob negotiated a key on the previous connection, all the stuff they send is encrypted. So the rendezvous point up there can't read anything, doesn't know who's talking. So all he's doing is passing bytes back and forth. So we've split up the roles here. The introduction point can be a system that doesn't have much bandwidth, but it's living on the Cook Islands or whatever. And the rendezvous point can be in New York City, and it can have really high bandwidth, and it has no idea who's communicating to who. So far, so good? Okay. Yes? Okay. At this step, when Alice sends the rendezvous point and I'm Alice, she also sends G to the X, the first half of a key exchange. And then at this point, the first thing Bob sends to the rendezvous point is, I want to talk to this cookie, which is Alice, which is just a random 20-byte thing, and here's my G to the Y. And actually, at this step, another detail, she sends the G to the X encrypted to Bob's public key. So nobody but Bob could possibly have been producing something that generates the G to the XY that they're going to use to talk back and forth. So Alice gets authentication to know that she's talking to the Bob she means to be talking to, and they share a key. And then the rendezvous point just passes stuff back and forth. So far, so good? Okay. Okay, so that's all well and good. Is this stuff secure? Is it more secure than the last stuff we've been talking about? Periodically, people come up to me and say, I've been working on this system called Invisible IRC, or any other number of Peekabooty or 6.4 or so on designs. And they always say, I've built this totally anonymous system. You can use it and you're 100% guaranteed to be secure. And my response is, well, against what adversary? What are we trying to do here? And by the way, what do you do exactly? What exactly is your protocol? And it's hard to tell in a lot of cases because they've never written it down, and it changes out from under you as soon as you come up with an attack that works. So nobody really knows how lots of these protocols work. In the case of Tor, we have a specification which we've written down, and you can read it and attack it. And several people have attacked it successfully, and it's been changing, but we've been documenting each part of that. Okay, so how do we actually compare this sort of thing to another system like Peekabooty or Freenet or JAP or Anonymizer? There are many ways of comparing anonymity, and this is an ongoing, hard, open research question. But one way we can imagine is, imagine the adversary owns C of the N nodes in the network, and he can choose which ones those are. So you might model this as the CIA has a limited number of Guidos they can send out and break kneecaps. Or maybe there's a limited number of subpoenas they can issue at one time, or maybe they are really good at breaking into FreeBSD boxes, but not anything else. And there are C FreeBSD boxes out there. So imagine there are C nodes, and he can choose which ones out of the network he breaks into. What's the chance for a random Alice talking to a random Bob that the adversary wins? And by wins, I mean learns that it's Alice talking to Bob. So in the case of Freedom and Tor, the adversary needs to be able to observe the first node, because that way he knows who Alice is, and observe the last node, because that way he knows who Bob is. Now, we're a low latency system here, so timing attacks work, between the first node and the last node. And if timing attacks don't work, then packet counting attacks work. There are a million traffic analysis attacks if you can see the first node and the last node that let you confirm your guess. But notice that I say confirm, traffic confirmation, not traffic analysis here. If the adversary only sees the first one, he doesn't know which of the exit nodes he should be observing to learn about Bob. But if he happens to guess Alice probably chose number 1 here and probably chose number n here, then he can look at both of them and confirm. So in this case, there's a C over n chance that he is able to observe the first one and a C over n for the last one. So in some sense, the security property here for Tor and Freedom is C squared over n squared. Now there are some other designs like Peekabooty and 6.4 which are more peer-to-peer and they're more spread out. The basic idea for lots of those is you go to the first hop and you say, hey, can you like make a circuit for me? And then the first hop says, sure, I think I'll connect to this guy. And then that guy says, I think I'll connect to this guy. And then after a while you have a circuit. And if the first guy you picked was bad, all the rest of them are going to be bad because they're going to innocently say, how about that guy? How about that guy? And then you're screwed. So the chance that the adversary wins at this point is C over n. If he owns the first node you've got, you choose, then that's it for your anonymity. And then there are some other systems. JAP, has anybody heard of the Java Anon proxy? A few people, great, okay. So there are a number of ways of doing JAP. The basic idea is that rather than using a free route network like I've been talking about, where Alice says, I want that one, and that one, instead you have a cascade where everybody goes into the first one, and then everybody goes to the second and third, and then out. And this is really nice because you're aggregating a lot of traffic. But since it's low latency, then you're not actually getting as much security as you want to because you just watch the first one and you watch the last one, and then you're able to break every single stream going past it. So that's JAP if you use only one cascade. If you use a bunch of cascades, then it's closer to Tor because you actually do have to observe both the beginning and the end of the system that of the cascade that Alice happens to use. So it's just the C squared over n squared thing, except if you use a cascade of length 4, the 2 middle nodes are never ever worth looking at in any of the cascades because they're never going to tell you about Alice and they're never going to tell you about Bob. So there's a factor of 4 decrease in your security. So to put some actual numbers on this thing, imagine the adversary owns 10 of the 100 nodes. So in the Tor case, he's got a 1% chance of winning. In the Peekabooty case, he's got a 10% chance of winning. And in the JAP case, he's got a 4% chance of winning. And just to put in the single hop proxy to compare things, I've got an anonymizer here. The anonymizer is a single hop proxy. There's only one of it. If the adversary owns it, then you're totally screwed. If the adversary doesn't own it, meaning isn't watching both sides, then you're totally safe. So it's a matter of what sort of threat model you're looking for. Okay, yes? Yes. Okay, so the question is, isn't that an unfair comparison? Because for Peekabooty, n is going to be really large. So maybe C over n is still going to be a better probability than the C squared over n squared for Tor, where n is just 30. Maybe. A lot of the designs that people are looking for peer-to-peer systems are aiming for safety in numbers. And you're right, if you get an n of 10,000, then assuming C is fixed somehow, then you're going to be in pretty good shape. But if the way Peekabooty scales is by allowing the adversary to sign up as many nodes as he wants to, then you're in bad shape. And I would really love to find a C squared over n squared design that scales well, that can be peer-to-peer. If there's some way that you know to allow me to add a whole bunch of nodes without allowing the adversary to add a whole bunch of nodes also, I'd love to chat about it. Because it's true, Tor doesn't scale as well as it should, and Peekabooty scales just fine but has crappy security. I'd like to find some compromise between them. Okay, so there are a bunch of trade-offs here that I can chat about, and we can chat a little bit more about them afterwards. One of the issues is low latency versus high latency. I talked a little bit about high latency systems. We've got an email-based remailer system called Mixminion, which is aiming for the other side of the spectrum. But Tor is so that there can be some way of web browsing and so on. And using Tor for web browsing and AIM and SSH and so on is a lot more popular than using Mixminion for email, because most people don't actually want to wait 2 or 3 hours for their mail to go through and then not know if it did. Whereas if you're sending mail through Tor, you anonymize your connection to port 25, and then you say hello, and it says, yes, I got your mail. So you can anonymously send mail and be quite certain that it got through. Whereas with Mixminion, it's you throw it, and hopefully it gets somewhere. Packet level capture versus stream level capture. In the Freedom case, they put in a shim on one side, and and basically it captures all the packets. And then it tunnels them to the other side and puts them out onto the network. So this means you can ping over Freedom, or you can play Quake over Freedom if it were fast enough and reliable enough. Whereas Tor only supports TCP connections. We don't let you do pings or Quake or something like that. And that's really nice for portability, because we don't have to deal with any kernel stuff or root stuff even. But it's not so nice if you want to handle any sort of protocol. So that's a trade-off that we made. Another one, every time I talk to people about this sort of thing, they say, well, can't you just pad? Can't you just send a lot of dummy traffic, and that way nobody knows what's going on? So that's a complex research question also. The short answer is no. One of the big reasons why we can't do that is because nobody's actually going to want to handle the traffic. All of these servers are volunteer servers, and if I say 1 gigabyte a day, they say, well, okay, it's for a good cause, I'll do it. And if I say half a terabyte a day, they laugh at me, and that's it for my volunteer servers. And Freedom found this out the hard way, because they actually implemented and installed padding for a month. And then they got their ISP bill of like $300,000. And they said, let's come up with a better design that doesn't involve padding. So I'd like to be able to produce some sort of padding to improve the security, but it's not clear how to do it. Also, even when you use padding, there are active attacks where the adversary stomps on one side and then the padding stops over here that allow the adversary to win, even when you're using full padding. So that's a tricky question. Another one is user interfaces. I've been talking a lot to people about usability and security lately. Tor has no UI. It runs as a daemon in the background. You never see it. You never care about it. It runs as a SOX proxy effectively, and you point your Mozilla or your SSH or whatever at it. So there's nothing to configure or deal with. You can edit the configuration file, but it works fine out of the box, so there's no need to change it for a client. On the other hand, when something bad happens, there's no way for me to communicate that back to the user. So I've been playing with different ways of maybe patching Provoxy so I can send it a message which it displays in your browser, but that won't work for SSH. And I've also been playing with different ways of maybe attaching some sort of external thing so you can talk to it and ask, where do you just build that circuit to? And it would tell you, so maybe we can display it graphically and people might like that. So the UI question is a tricky one. I get the feeling that having no UI is somewhere in between having a good UI and having a crappy UI. So I'm doing okay, but I'd be happy to chat with people who are good at writing GUIs so that we can add something to this. So another issue is at the AS level on the internet, there are lots of different ISPs that are able to observe various pieces of your path. We've been doing some research lately to look at all the ASs that Alice traverses between her, say, client modem machine and node number 1, and then also all the ASs that the exit node to Bob the web server traverse. And in a lot of cases, there is one ISP which is on both of the paths. So if you go to level 3 and install a little black box sniffer or whatever, you're going to break about 1/3 of the Tor traffic just by being able to do traffic confirmation one side to another. So we might somehow want to do some way for Alice to say, I'm nearby that Tor node, so I'm going to connect to it first. And my web server is nearby that Tor node, so I'm going to exit from there. And that way I will travel over the internet as little as I can when I'm not on the Tor network. On the other hand, it's actually kind of tricky for Alice to know what ASs will be traversed from her exit node to Bob the web server without being in either of those places. So that's a hard problem. Another issue is incentives to run servers. So far, this is a volunteer-based infrastructure. Freedom started out saying, we will give a cut of all of our profits to all of you, and we'll pay you for the bandwidth, and it'll be great. And then they shut down the server because they didn't make enough money to do that. So my approach to this so far is that there isn't going to be any money involved. It's free software, it's going to be volunteer-based, and we'll see how far that gets. Because as soon as you start involving money, then everybody wants more than they're getting, and there's never going to be enough, because users are not going to pay for a system like Tor. If people are willing to pay at all, they're going to pay the anonymizer, their $10 a month or whatever, and that'll be that. So we've got volunteers, we've got 30 of them. We're adding servers every month. Hopefully we'll make it up to 40 or 50 or 60, and who knows. If you want to run a server, I'd love to talk with you. Basically, if you've got 1 megabit in each direction, we don't actually use all of that yet, but we like it for handling spikes. Okay, so enclave level onion routers. When you're talking to government folks, they don't want to install this anonymizer on their machine and then have everything protected from then on out. Because they don't want the random engineer working at the Navy to have encrypted anonymous communications out of the secure classified area. That sounds kind of dangerous to them, and I can understand that. So the way that they want to run this thing is you put the Tor proxy on the firewall, and everybody uses it in plain text from their machine inside your classified area to the firewall. So that means that all the people you want to, all of your employees that you want to observe, you can observe them just fine, just like you do now. Yet the external communication from your company or your .mil installation or whatever is still private, secure, traffic analysis resistant, whatever you want to call it. Yes? Sure. It certainly could be, and that should be built in just like it's built in right now, because presumably you've got filters right now to say that's going to Kazakhstan, packets shouldn't go there. So you should be able to do exactly the same thing, because it's all in plain text and you can filter it before it even shows up. Yes, you run a Tor proxy on your firewall, and then all the traffic goes there in plain text and you're all set. Okay, so we've been talking about enclave level paths. Path length. This is a hard question also. All of these are hard questions. Anonymity is a really hard problem, and we've been working on just the basic parts of it for now. So far, what we're using is 3 hops, and I can give you a very basic security argument for that, but nothing more. Imagine you're using only 1 hop. Clearly this is bad because that 1 hop can see Alice and Bob. Okay, so you want to use 2 hops. And when you use 2 hops, then the adversary has to see both of them, has to see the first one and the second one. And if he can do both, then he knows Alice and he knows Bob. So the traffic confirmation attack is the tricky attack here that we're not going to try to deal with. If the adversary sees the first hop and the last hop, we give up. So what we want to do, if there are any attacks that are harder than seeing the first hop and the last hop, we don't care. Go ahead. You can do them. If there are any attacks that are easier than seeing the first hop and the last hop, then we need to solve those so that the traffic confirmation attack is the best attack against the system. And imagine if paths are all 2 hops, and you use the Italian mafia for the first hop, and then it goes to the French mafia. The Italian mafia knows that you've only used 2 hops, and he knows that if he makes a phone call to his buddy at the French mafia, he's going to learn where you're going. So maybe the attack there, maybe it's easier to make a phone call than it is to do traffic confirmation. Whereas if you use 3 hops, then the guy at the Italian mafia doesn't know who to make the phone call to for the 3rd hop. So he doesn't know if it's worth it to pull in the favor for the 2nd hop to find out about the 3rd hop. So it's a compromise. And pushing on the other side is you don't want anything, you want as small a path as you can manage, because every time you add another node, it becomes slower and slower and less reliable. So on the one hand, we've got more nodes is good, and on the other hand, we've got fewer nodes is good. So 3 seems like an okay compromise for now. And I'd be happy to chat more about that also. And then the last issue, P2P network versus static network. We've been talking a little bit about that here, and we can chat a bit more about it later. It would be nice to be able to scale this a little bit better. Yes? The question is, can't you just let the client decide and everything will work out? I can let the client decide, but I should give you some recommendation or maybe make some decisions about which ones I think are most secure. I'm pretty sure that 5 hops is no better than 3 hops. So I can let you decide, but I would recommend that faster is better. But I mean, yes, you could use 5. That'd be fine with me. On the other hand, you're loading the network down more, so maybe 3 is a better choice for the rest of the world. Okay, so there are plenty of future work issues here. One of the ones that I should talk about for the government folks here is that we're going to get this common criteria certified one way or another, because nobody in the government actually wants to use it until we can call it secure, whatever that means. And there's a bunch more theoretical work. Okay, so you can fetch it from freehaven.net/tor, and it works right now out of the box, and I'd be happy to help people actually make it work if they can't, because hopefully it's very easy to make work. And it comes with a specification, a design document. The JAP folks actually implemented a Tor proxy in their JAP software. So now there are 2 things out there, and that's because we actually have a spec so that they knew what to do. Because I've been bugging them for a spec for a really long time, and they said, we have this web page, but it's in German and it's not very good. So, okay, I don't know how JAP works actually. So, yeah, ask questions. So the question is, what if half the computers were run on PCs on client modems or whatever, and you turn them off at night? How bad would the network become? We can handle nodes going down pretty well. Certainly for people browsing the web, they don't care if a node is down, because you immediately learn that it's down and you don't try your web request over it. If you're IRCing over that node, then you want to keep your IRC up for days on end. So probably you want to start using a circuit that is not likely to go down, and we've been working on heuristics to guess whether a circuit is likely to go down, but we don't have those worked out quite yet. So in terms of having computers that go off sometimes, that's fine. In terms of having computers with crappy bandwidth, if you're going to be pulling down your huge file, you really want to use a circuit with good servers. So we've been working on heuristics to try to guess which ones are going to be crappy bandwidth and which ones are going to be good, so you can build your circuit over the right ones for the stream you're about to use. But it's a hard problem. Other questions? Yes? Excellent. We have a testimony right here. Yes? So the question is, the goal here is to not have a single point of failure, but we still have this Tor proxy thing, and isn't that a single point of failure because there's only one of it and it knows where you're going? It's running on your computer. So your Mozilla is a single point of failure, and your keyboard is a single point of failure, and so on. You have to trust that your computer is safe. There are no external single points of failure is the goal. Okay, so you're saying if we use the enclave model where the Tor proxy doesn't live on your computer, but it lives on your company's firewall or something, then somebody inside your company is still able to break that communication. Yes. If you want to be able to observe the communication, then other people have to be able to observe it too. If you really want security inside your company too, then you should run the proxy on your local machine, and then your IT department can't sniff your traffic. Some people like this, some people don't. We had an installation of Tor at the United Nations for a week. One of my friends who's a sysadmin there put all the traffic for his division over Tor for a week, and nobody noticed, which is pretty nice. There are some other companies out there and government installations which are using this so that they can get around the firewalls and so that they can get around the fact that their IT department sniffs them all the time. Other questions? Yes? Have there been any legal issues yet? Any subpoenas and so on? No. We've been waiting for the first abuse complaints, and so far nobody has done anything too bad with it. Many of the exit servers are in situations where they have lawyers all set up, and they're just waiting for the subpoenas to come in, and nothing's happened yet. And I consider that a good thing. It's a statement that humanity is nice, at least for now. Other questions? Yes? So the question is, I'm stuck behind a really restrictive firewall in my company, and I want to use Tor on my computer. Currently, no, it won't work, because it needs to connect out to port 9001 on various places around the internet. What we've been working on, though, in the background, because nobody seems to want this too much yet, is tunneling Tor over HTTP. So now all of the Tor servers out there will act like they're web servers, and you can act like you're making an outgoing port 80 request, just like you tunnel all the protocols over everything to get out of your really restrictive firewall. So too could you tunnel Tor. Other questions? Yes? Okay, so the question is, tell me more about that onion routing patent, because it seems like you're still doing onion routing. The onion routing patent is for, let's see. So the onion routing patent is the concept of building up a layered data structure and sending it into the network in order to deploy a circuit. We are not building up a layered data structure to send it into the network to deploy a circuit. We're using a totally separate design which builds the circuit one hop at a time. It's a subtle thing, but for purely technical reasons, we had to extend the design so that it happened that we weren't covered by the patent anymore. Yes? I'm not breaking that company's security policy, the employee is. I'm just writing software. Some people need this software if they're living in Iran and they can't get around the Iranian firewall, or maybe they're living in some, there are many situations. I'll go back to the beginning. Okay. So you're, yep. This particular piece of software is not unique in that property. So because it has very useful uses, I'm okay with potentially allowing your employees to violate your security policy. But you can provide the same sort of security for your company by telling them, we're running one of these on the firewall, and you can send your SOX connections to it, and they will be securitized, privatized, anonymized. Yeah? Unless you tunnel through port 80, as we were talking about, which we haven't implemented yet. So. Well, every time I talk to people in Guatemala and so on, they say, we are only allowed to connect to port 80, and it better work. So if we want this sort of thing to be usable by dissidents around the world, then we need to implement that feature. Yes. It's you keep asking anything for me, here's something from me, anything for me. So it will slow it down, but hopefully not too much. Yes? Yeah. I'm not sure I understand the question. Yep. So the Privoxy issue is on a separate level. I'm talking here about location anonymity, hiding the IP that you're coming from. Privoxy is talking about data anonymity. It's talking about not giving out the exact version number of your browser and so on through the channel that I'm making. So that's on a totally separate level. Yes? They are resolved by your Tor client locally. When you pass the address to the Tor client and say, please connect me to this thing, it looks at it and says, that ends in .onion. That's special. And then it goes off and fetches the descriptor and goes through the whole thing. So you need to use something like Privoxy, which speaks SOCKS 4a to do that. The difference here is when you're using just normal SOCKS, then your Mozilla resolves it first and then passes the IP to the Tor client. And obviously your Mozilla can't resolve the .onion name. Okay. Privoxy works on Win32. Yes. Yes, but it's got a snazzy installer, I'm told. You really do want it for web surfing also, because when your Mozilla resolves the IP and then you tell the IP to your Tor client, from the outside world you say, hey, what's the IP of google.com? And then you anonymously go somewhere. And that may not be what you had in mind. You should grab and install Privoxy, and it should solve that for you. Question in the back. Yes. Assuming they have non-crappy bandwidth, that would be a fine thing to add. If they have non-crappy bandwidth, maybe it's okay to add them as exit servers also, because the entry point is the one that really matters for identifying Alice. Or maybe it's okay to add them as entry point but not exit point. Or maybe it's okay to add them for both if the adversary, if the user says, C over N is good enough for me, I'd like a large N, I'm happy with using them everywhere. So it really depends what you're looking for. Any more questions? Yes? Pardon me? Could you grab the .onion domain? I imagine it's hard to register a top-level domain, right? Good question. We should chat about that. If you're set up correctly, meaning you're using Privoxy, then you're not leaking the fact that you're trying to resolve it. If you're set up incorrectly, then yeah, you're trying to resolve foo.onion, and it says, that has no IP, what are you talking about? So if you somehow broke into a DNS server and listened to requests for .onion, then you would hear from the people who are misconfigured. Yes? You wouldn't be able to learn where those proper servers are. Because just because you have a foo.onion address doesn't mean you know where it should resolve to. Those people are anonymously connecting out, and they never reveal their IP. We should chat more about that afterwards. Any final questions? Okay, I'll be outside if you have more. Thank you.